I will tell you about the magnetic field in a current carrying solenoids and also the magnetic field in the toroid. So first I am taking the magnetic field due to the current carrying solenoids. Actually the question in the board is oftenly asked on the basis of this solenoid. So first they ask that what is the solenoid, and then they ask that what is the ideal solenoid, and then they ask find the expression for the magnetic field when the current passed in the solenoid. So this is the complete question that is asked in the board exam. Magnetic field in a current carrying solenoid. So now first is what is solenoid? Solenoid means when a insulated copper wire or conducting wire is wound in number of turns along the length of the cylinder, non-conducting cylinder, then this is called the what we have this solenoid. So this is in the form of the spiral. So this is the spiral form of the solenoid. If insulated conducting wire is wound in number of turns along the length of non-conducting cylinder. It is called solenoid. It means what? That the solenoid is in spiral form. So this is like this one. This I take. This is suppose the wire that is wound here. This is coming out like this. This is now a solenoid. It may have the turns like that when this is taken outside. So this is the winding like this that I have told you this. This is now in this way. And if suppose I bind it like this, then I can have this another form. and in this is like this one. Then this is from outside, this is from inside like this, and this is from outside like this. When we are having this kind of form or this kind of form, then this is the solenoid. Solenoid. When the current is passed through them, then a magnetic field is produced along the axis of the solenoid. Because we can assume that each of the solenoid, each of the turn is in the circular form, and we know that when the current is passed in the circular coil, the magnetic field is maximum at the center. So if there are number of turns in series and then we join the line, then we join the centers of the different turns, that will be the axis of the coil, and that magnetic field will be maximum at the axis of the coil. So when the current is passed in the solenoid, there is the magnetic field inside the solenoid. So now we can have, let's suppose this is this I am taking now like this, current is, so this is in this way, the current is in this way, this wire is taken from outside like this, so this will be going in this in this way. This is now your anti-clockwise. Then this is now north pole. If the current at the end of the solenoid appears to be anti-clockwise, then this will be the north pole. If the current, then definitely the other end of the solenoid will be the south pole. If at one end of the coil of the solenoid the current appears to be clockwise, then this will be the south pole. So what we have here, this is like this, the current is in this way, then this is now your south pole. This is now south pole in this way. So if we are having the current in this direction here, then this will be the north pole and this will be the south pole. If we pass the current like this and it is going away from this line, then this is now what? In the south pole. So this will be now south and this will be the north. So in this way, this whole of the solenoid produce the magnetic field inside it. Now then a question is asked, then what is the ideal solenoid? If the diameter or thickness of solenoid is negligible in comparison to the length of solenoid, it is called ideal solenoid. When the thickness or the diameter of the coil, is very, very less than the length, then this solenoid is called the ideal solenoid. When current is passed through the solenoid a magnetic field is produced inside it along the axis of solenoid. Along the axis of solenoid. Each turn of solenoid is circular. In which magnetic field is maximum at the center. So just you join all the centers of the solenoid of this circular turn, that will make the axis of the solenoid, and in that case the magnetic field will be along the axis of the solenoid. When all centers of all circular turns are joined, it will be the axis of solenoid. So magnetic field due to this solenoid is always along the axis of the solenoid. And let's now I am taking this the solenoid in this way. Better to take it like this. This is now from inside, then to this. This will come in this way. Suppose this carries the current I. Then this current will be like this one. And then to this one. This is the axis It is the axis. Axis of the solenoid. Then definitely this will be the north pole and this will be the south pole. So magnetic field will be along this direction. This will be the magnetic field. This is the magnetic field B along the axis of this circular coil of this solenoid. And let us take a rectangular path like this. Suppose this rectangular path is this is now suppose your P, this is now your Q, this is R and this is S. So now what we have? Let N equal to number of turns in solenoid and L equal to length of solenoid. Then what will be the number of turns per unit length? Number of turns per unit length. This is equal to N. It means what? That this N equal to N upon N. And let I is the current that is passes through this one. So for the application of the magnetic field for the Ampere's law, we have to assume a rectangular closed path. And let this PQ is of length L. So number of turns in length L. Let L equal to length of rectangular closed path. So that is equal to PQ. Equal to PQ. So now we have number of turns in length L. This is equal to N into A. So now what we are having? Construct a closed loop P, Q, R, S called the Amperian loop. Called the Amperian loop. Then we can apply the Ampere's law. So Ampere's law equal to, this is now your B dot dm equal to mu naught summation I. This is the Ampere's law. That we will apply this for this loop. So now this is from P to Q. B dot dl integration Q to R B dot dl plus integration r to s B dot dl plus integration, this is now your s to p, this is now your B dot dl, this is equal to mu naught into n l I. Now what we have, this summation I is equal to n l I, n l I. Now in each term the current is I, so the current is so much terms, that will be equal to NL into I. So in place of this sigma I, we will use this NLI. So now you can see from here that this integration P to Q, this is now your BDL cos 0 degree. Now plus integration Q to R. This is now your BDL cos 90 degree plus, now since this side RS is outside this solenoid, so there is no magnetic field here. So this integration becomes equal to now 0, and then we are left with integration, this is now your S to P. This is now your B dl cos 90 degree, and this is equal to n mu naught n l I. Mu naught n l I. So this being the 90 degree, this being 90 degree is equal to 0, and this is already 0. So we are left with the first integration. Now we are having this integration P to Q B dl. Now remaining all are 0, 0, 0, 0 equal to mu naught n l I. So this is equal to your B integration P to Q. This is now your dl equal to mu naught n l I. So this is now B into L, this is equal to mu naught n l I. So now L will cancel from here, then we are having this B equal to mu naught n I. This is now magnetic field. So now magnetic field outside the solenoid is 0. Magnetic field outside the solenoid is 0. This is why that this third integration has been taken equal to 0, because of this factor. So now you can have that this B equal to, or B equal to mu naught n I upon L. This is now another form. We have used this n equal to n upon L. So what we are having, this B is directly proportional to the I, the current. So B is proportional to N, and it's a number of turns, directly proportional to number of turns. L, directly proportional to 1 upon L, the length of the solenoid. The bigger the solenoid, then the number of turns will be same one, but this magnetic field will decrease. So for higher magnetic field, the number of turns must be as much large as possible, and the length of the solenoid must be as low as possible. So now we can have here this B is proportional to I. So now if we are having this magnetic field, this is now suppose your B, this is now your I, then we are having this. This is now B proportional to I. Then the number of turns and the length, this B is proportional to N. This we can see the same. Small n, or this, suppose we are having this capital N, then you can also increase to this one. So now here we are having the variation like this. B, and this is now N. Since the number of turns cannot be equal to 0, at least there will be one turn. That is the one the circular coil of one turn only. It means that this will lie somewhere else from here. So this shows B is proportional to N. And then what about the length? And then we are having to this. No, this line will not be like this. This is line like this. B proportional to N. Now then third we are having B proportional to 1 upon L. So if we are having this, the variation of this B with the length of the solenoid, this, then this will be in this way. Now B is proportional to 1 upon L. So for maximum field inside this, and you can see from here that if suppose number of turns are not increased, but the length of the solenoid is increased, then magnetic field will decrease. And if suppose the length is decreased and number of turns are kept the same, then this magnetic field will increase. So this is what, that by changing the number of turns, providing the length is the same, the magnetic field can be increased. And if we are having the same number of turns and the coil is expanded or this is the contracted, then in both the cases the magnetic field will change. So also to be depending upon the length of the solenoid. So this is no meaning that if somebody says that this is independent of the length, this always depends upon the length of the solenoid. And now magnetizing field we can see here. Magnetizing field. Field H equal to B upon mu naught. So H equal to Ni, or this H equal to Ni upon L, like this. And you can see from here that if suppose there is something inside the coil, suppose we insert a iron rod, then what will happen? This magnetic field will increase. Since iron is a ferromagnetic material and it will magnetize immediately, So magnetic field increases when some material is kept inside the solenoid. For medium inside the solenoid, this B equal to mu naught into mu r Ni. Mu r, the relative magnetic permeability, where mu r relative magnetic permeability. So what we see that for iron, for ferromagnetic, materials, now this mu r is very greater than 1. This mu r is very greater than 1. So magnetic field inside the solenoid will increase if a ferromagnetic rod is placed inside it. And for paramagnetic this will be also increased, but that will not be so much high. In case of this dimagnetic, this will decrease. So if we place a dimagnetic material, then this magnetic field will decrease. And for paramagnetic, mu r is greater than 1, and for dimagnetic mu r is less than 1. So by having this dimagnetic material inside this solenoid, the magnetic field will decrease. By inserting a dimagnetic material in solenoid, the magnetic field will decrease. So this is the effect of the materials which are kept inside the solenoid. And now after this solenoid we are taking this toroid. magnetic field in a toroid. So first the question is asked that what is the toroid? So when an ideal solenoid is given the shape of given the circular shape, then this is called the solenoid. When an ideal solenoid is given a circular shape, it is called toroid. When the current is passed in toroid, the magnetic field is produced inside the toroid along its axis. So what is the axis of solenoid? That is the axis of this toroid, because we are making the toroid from this solenoid. So now we are having, let n equal to number of turns in toroid and r radius of toroid. So this is in this form that I sketched this diagram. This is not right one. And I take another circle and let like this. Then let this current is passing through it. This is now I, and we are having these centers. So combine to all these centers of this circular coil of this solenoid. This is now suppose the center O. Then this so much distance. This is the R, the radius of this solenoid. This is the solenoid. Because solenoid is itself a closed loop, so we apply the Ampere's law directly. Toroid is itself a closed loop. So Ampere's law, integration B dot dr this is equal to mu naught summation I. Now how to find this summation I? This is equal to integration over the closed path b dl cos 0 degree is equal to mu naught ni. What we have, this summation I is equal to ni. Now each turn carries a current I, so n turns will carry the current ni. So this summation I will be replaced by ni, and this is now your b integration dl, this is equal to mu naught ni, and b, this is now equal to 2 pi r equal to mu naught ni. Now this integration is equal to the length of the circumference, so this b is equal to mu naught ni upon 2 pi r, or we can have this b equal to mu naught ni, where n equal to n upon 2 pi r, number of turns per unit length, number of turns per unit length. So you see that this expression is same as that of the solenoid also, but the number of turns are different. Here this number of turns per unit length, this is equal to n upon 2 pi r, the circumference of the toroid. But in case of solenoid, this is equal to n upon capital L, the length of the solenoid. So this is the difference one. And the magnetic field only inside this toroid. If this space or this outside of this one, the magnetic field is always 0. The magnetic field outside the toroid is 0. वहाँ मैग्नेटिक फील्ड जैसे हमने टॉरॉइड बनाया तो उसके बीच में एक स्पेस था, तो वो इस स्पेस में भी मैग्नेटिक फील्ड 0 होता है, और उसके बाहर भी अगर मैग्नेटिक फील्ड लेंगे तो भी ये 0 होता है. तो मैग्नेटिक फील्ड इज ओनली इनसाइड द toroid. Out of that, the magnetic field is always 0. So this is about the magnetic field in the toroid. So I have told you the magnetic field due to the current carrying solenoid and that current carrying toroid. Current carrying toroid. So this is the question is asked either this based on solenoid or based on the toroid. So thank you very much.